Alright, we're having another free response video, and this time it's a related rate problem involving volume. And you've got this triangular looking trough over here that they tell you is isosceles triangles, as you can see over here. And the base says 2, and the height of this thing when it's inverted is 3 feet. And let's see if we can make some sense out of this. So the first part A, asks you to find the volume of the water in the trough when it's full. So that's just basically the area of the triangle times the length of that trough, and when it's completely full, it's 3 feet high. So I guess we could just say the volume is equal to 1/2 of the base, which is 2, times the height, which is 3, times the length, which is 5. So it doesn't ask us to talk about any units. Well, it doesn't hurt to put it in there. It doesn't ask us to convert to gallons, thank God. So we have 30, half of 30 is 15. So we have 15 cubic feet of water in that trough. And part B starts talking about calculus stuff, because it says, what is the rate of change in H at the instant when the trough is 1/4 full by volume? So, well, we know that this is the volume right here when it is 100% full, right? So the volume we need is, for part B, we're interested in the volume when it's 15/4 cubic feet. And what else can we get out of the statement? Water is being siphoned out of the trough at a rate of 2 cubic feet per minute. So that's going to be the dV dt. And since it's being taken out of the trough, put a negative sign in front of that cubic feet per minute. Alright, and let's see. So we're interested in finding dH dt, and we're given this, and we know the volume formula. So we need to, and we know that this 5 feet is going to be, the length of that is going to be consistent, right? And let's just take a look at the triangle for a second. Just focusing on the triangle portion, that's 2, and that's a height of 3, right? So let's talk about the volume. Let's just write the formula out real quick. Okay, so the volume is equal to the base times the height divided by 2, and times the length of 5. I'll just put it like this. So right now, if we take the derivative, we will get, we'll have to do a product rule, and we don't know what the change of the base is. So let's just think about this triangle for a minute. It's going to be a proportional triangle, because let's say that the water is only this height right here. The base is going to be proportional to the height at which it is. That base is shorter and this height is shorter, right? So it's going to set up a proportion. So let's just write a proportion over here. We have the base to height is equal to 2 to 3. And remember, since we're looking for dH dt, we need to solve for the base in terms of the height. So just simply cross multiplying here, or multiplying both sides by h. That cancels, and we get that base is equal to 2/3 of the height. Okay, now we're going to substitute into our volume. Before we even take the derivative, we know that the volume is equal to 2/3 of h times another h times 5, and then what else do we have? Down on the bottom we have that 2. So we have 10, the number is 10 over 6 h squared, which can reduce to what? Let's see here, we have 5/3 h squared. So now when we take this derivative, we only have one variable over on the right side, so that's a pretty desirable thing. So let's just go ahead and take the derivative, and then we'll use our information that they want us to know. What is the rate of change when it's 1/4 full? So let's just take the derivative. We have dv dt is equal to 10/3 h dh dt. Okay. Alright, we know dv dt. We're trying to find dh dt, and we need to find out what our value of h is in this problem. So let's go right back here to this statement here. Well, actually, the statement right here is all we need. We know that the volume 15/4 is what we're looking for, so let's just substitute it into this equation right here. Equals 5/3 h squared, and that'll give us our height when the trough is 15/4. So if we multiply by this 3/5 on both sides to cancel out, we get h squared, and looks like we can make that a 1 and make that a 3, and so the height is equal to 9/4, and we take the square root of that to take care of that h, and this is equal to 3/2. Sorry about that, 3/2. So now let's plug in our height into our derivative, and we can solve for dh dt. Let's go back and make sure dv dt right here is -2 feet per minute. So we'll put that in, -2 equals 10/3 times 3/2, that's our height, and that gives us dh dt. Now we could clean this up certainly before we move it over. That's cancels out, and that becomes a 5. So we just need to take -2 divided by 5, and our height looks like it's decreasing at -2/5 of a foot per minute. Okay, so you probably want to restate the question. What is the rate of change of height? So you can say, say the rate of change of height is -2/5 of a foot per minute when the height is 3/2 or a 1.5 feet, or you could say when the volume is 1/4 full. Either way, when the height of the water is 3/2. And that should be plenty right there. Alright, so that's part B, not too bad once we got everything in terms of H. And then finally, part C wants to know what is the rate of change in the area of the surface water, the surface of the water shaded in the figure at the instant when the trough is 1/4 full. So it looks like this little section right here. Okay. So they also want to know it when the volume is 15/4, and we already know that the height is 3/2, right? So now our only question is, what is the formula for area right there? The surface area is just, I guess it's just the exposed portion of the water right here in the trough. So let me erase part of this so I can refer back to the figure if I need to. Okay. Alright. So let's write down a few things here. First of all, in part C, they do want us to find dA dt. And we want to know that when the height is equal to 3 over 2 feet. And it looks like if I just sort of draw a little figure of the shaded area that they had right here, the length of this is 5. And this portion looks like the base of our trough. So let's write down that area is equal to, area is equal to 5 times the base. And of course we know what the height is when it's 3 over 2, but we know the ratio of base to height is 3 to 2. So that means that the base is equal to 2 to 3, right? So let's just go ahead and solve this here. So the area, and this is in terms of, let's see here. Actually, we need this 2/3 of height, right? So we're going to put that in here, that we have 5 2/3 of h, and the area would equal 10 over 3 times h, and then if we take the derivative, we get dA dt is equal to 10/3 of dH dt. So if we were left it in terms of b, we would have another unknown variable, dB over dt. So if we would have taken the derivative right here, that would have been dA dt is equal to 5 dB over dt, and that would have done us no good because we don't know what dB over dt is. And since we found dH dt in the previous problem, and it was -2/5 if I recall, so dA dt is just simply going to be 10/3 times -2/5, and now what was our units here? We have this 10/3, which is in feet, and then we had -2/5 feet per minute. So looks like our units is going to be square feet per minute. So just cleaning this up, give them a final answer. -20 over 15, or we could simplify that, right? Make that 2. So it's going to be a -4/3 square feet. If I could write, I would be in business. Let's see here, we have square feet per minute when the volume is at 15/4 cubic feet. Alright, now let's talk a minute about the signs and stuff. Since there's no water being added, it's all being taken out, it kind of is intuitive that the rate of change of the area should be a negative quantity. As was the area, or excuse me, the volume, or excuse me, the height was changing at -2/5 of a foot per minute. So the water's moving out of there fairly rapidly, and looks like this answers all 3 of the parts. So I hope this is intuitive and helpful for you, and good luck with related rates.